momentarily. Hello, Internet, we're live.
Hey everyone, welcome to the 18th episode of the Stanford MLSys seminar series. I'm Curran. We have with us today Dan, Piero, Fyodor, and our guest today, Theodoros Rekatsinas, as he told me his name was pronounced. So this week we're going to be talking to Theo about some of the work that he's done around software 2.0 for data quality management. And a lot of this work is stuff that he's been working on for a while now. So we're very excited to hear kind of his thoughts around and the vision that he has going forward around some of these topics. And Theo himself is an assistant professor at the Department of Computer Science at University of Wisconsin-Madison, currently on leave at Apple. And he also co-founded a startup that is now part of Apple that looked at some of these problems around identifying correcting errors in data. So as always, Theo's going to give a talk for 30 minutes, and then we'll have a 30-minute podcast-style discussion where we'll ask Theo's questions, and you can put your questions in chat, and we'll try to get those across to him during his talk, and then, of course, during the podcast-style discussion. So Theo, take it away. Thanks so much for joining us.
Oh, thanks for having me over, and I should say that this is an awesome endeavor that you guys started. I know a lot of people enjoy this webinar, so it's a pleasure to be here.
Thanks.
Let me start sharing the screen. Wait. Okay. Can you see it fine?
Yeah, looks great.
Excellent. Okay, so as Karen mentioned, I will talk today a little bit about my experiences over the past few years around developing ML-driven or software 2.0 approaches for tackling data quality problems. And I'm gonna focus a little bit on, I'm gonna start with some history with a project that started at Stanford actually called HoloClean that was also the foundation for some of the projects that I'm gonna present, and also for the company that we started called Inductive. And let's get to it. So data quality. It's actually quite a hard problem that a lot of people are tackling, especially nowadays. We're focusing on analytics over massive amounts of data. So it is actually a huge pain point that a lot of people have to deal with it daily. And this involves upstream, for when you're dealing with heterogeneous data sources, you need to focus on manual labeling of your data, fixing mistakes in your data, try to do best effort imputation, all just to serve downstream analytical tasks, ranging from simple tasks like I want to estimate a mean, an average over a sample, towards making more complex decisions. And exactly because this is a hard problem, there is a huge ecosystem in the middle between upstream and downstream for tackling all these different problems that appear. This is just a small, more business-oriented, if you will, view of the ecosystem. You can see some familiar, old favorites like IBM and SAP and Oracle, focusing on problems that have to do with data preparation. And you have more like newer players and startups like Tamer and Trifacta, that are focusing more on specific problems like data integration, cataloging, and wrapping, and so on. So as some background, let me talk a little bit about the problems that we will be focusing today. So what are some data quality management tasks? Like two typical tasks are, you can split actually tasks into two categories. Error detection tasks. So in this scenario, you want to identify samples or entire tuples in a structured data set, let's say, that have mistakes. So in this case, the last tuple, it's completely wrong. You may want to identify specific mistakes in individual values. So you want to validate these individual values. Another group of tasks is to perform data repairs. Once you have identified these errors, of course, something is wrong. You don't want to push them downstream. So you may want to take some actions against mitigating these errors. And you want to, for instance, perform imputation, fill in some of these missing values, use information that you may have about the data set in hand to actually perform repairs, and so on and so forth. So the goal here of data quality management, really, at least through my biased perspective, is to deal with all these types of tasks And the goal is to automate these tasks. Now, if we come back a little bit to this pipeline of upstream data, downstream applications, one may ask, okay, why not just push all this low quality data to smart machine learning models? They will deal with all the noise. And as a reminder, just keep in mind that ML models are actually sensitive to this low quality data themselves. When you're training models, you have corruptions that can bias the model that you're learning. Think of poisoning attacks here that can completely change the model that you will learn. Or you may have inference, like problems at inference time, where the queries, the examples that come in have noise, and that may lead to wrong predictions. So I will talk briefly as to how we can also handle these types of problems and why we need to actually reason and fix mistakes in our downstream analytics. So my goal, if I'm to summarize it somehow over the last few years, is really to streamline data quality management. And we've done so with many different projects. I mentioned HoloClean already. Some more recent projects and in my group, Picket and Marius. Picket focuses a little bit more on ML, on data validation for ML pipelines. Marius is actually focusing on graphs and heterogeneous structured data. And the question that has been driving this line of work is really, can we automate data quality management? And what I will hope to convince you today is that actually if you adopt probabilistic semantics and rely really on self-supervised approaches that really learn a model as to how clean data looks like and how noisy data looks like, you can actually use these models to drive automation. And the key secret sauce, if you want here, the key ingredient, is really to reason about structured context to be able to learn these models and learn accurate models and make information theoretic and optimal decisions. So what do I mean by structure? Let me start with a very small example, a very brief example, easy to follow, just to give you a very high level description of what do I mean by structure. So let's take the simplest estimation task, downstream analytical task, mean estimation, right? I have a bunch of samples and I want to compute the mean over these samples. And I have a bunch of missing values. So standard things that data scientists will do here is that some of them may opt to impute some of these values with the mean and do a kind of a coordinate-wise mean and fill it in. Others may opt to remove these samples that have missing values completely and focus just on the samples that are complete. So in this case, if you follow the first approach, you'll get the coordinate-wise mean that looks like the first line. If you follow the second approach, you'll get a mean after filtering, that looks like the second line. And as you can see, there are significant discrepancies between these two estimates. However, I want to claim that actually you can do much better and you can have this improved estimate. And this estimate is actually better than any of the other two, where we're filling some of the values, and for the others, we're leaving them empty. And what I'm exploiting here to make this claim is actually some kind of assumption that might be apparent to some of you, maybe not. The fact that if you look closely, actually x1 is nothing more than the sum of x2 and x3. So there is this kind of linear dependency. And x4 and x5 are independent. So if we know this type of dependency a priori, you can actually use this type of context and information to obtain better results for your downstream analytical task. And what we did here really is to solve a very simple data quality problem by leveraging context. In fact, this, you can study this problem theoretically. Mean estimation and robust mean estimation is actually a very fascinating problem that people have been studying for a long time. Recently, we showed that if you follow this two-step approach, that first you use these dependencies and structure across coordinates of the data to fix these corruptions, and then you estimate after you have fixed the corruptions, you actually get information theoretic optimal error estimation in the presence of structure. just to go over these formulas, don't pay too much attention. What they really say is that you have this quantity when you have a very fine-grained corruptions. I can corrupt any entry in my data set, and I allow for alpha % of these entries to be corrupted. If I actually utilize my structure, I will get a much better error. Why? Because of this quantity MA, that it's telling me how many corruptions do I need to introduce to actually destroy the structure that is in the data. So the higher the structure, the stronger the structure, the more dense the structure, the larger the number of corruptions I need to introduce, and hence, the lower the error will be. So it's quite interesting, but in real life, you have heterogeneous types of structure. It's not just this type of linear structure that we study for the theoretical case. You can have arbitrary business constraints, right? For instance, in this scenario, you may have integrity constraints like functional dependencies that are domain specific over your data set, schema constraints, and so on. You may have external knowledge about your data, catalogs that need to be satisfied. And of course, you have dataset statistics that you also need to take into account. So if I'm to summarize basically the approach that all the systems that have been developing over the last few years follow is this one. You use this context, you want to reason about this context in a holistic manner to build really a generative model about your data that learns how to distinguish also between clean, learn how the clean data is generated, and also learn how errors are introduced. And once you have this model, this generative model, all you need to do is cast a bunch of data quality tasks, such as error detection or data repairs and imputation, as nothing more than inference queries over these models. So the whole premise here is, can I learn these models in a completely unsupervised manner, just by relying on the data that I've seen? And then if I can do that, can I very fast, run these inference queries? So to answer these questions and around this kind of principle, we have developed several systems here in red. FDX, which is focusing on discovering these types of constraints and domain constraints over tabular data and doing this kind of profiling that will allow you to know if you have enough structure to even automate data quality management. HoloClean here in the center, that focuses really, we started from probabilistic graphical models, the old school kind of machine learning. And then we saw that you can actually start using transformers to be able to automate data cleaning. So attention there is a key component of all the models around HoloClean. And later, more recently, we are focusing on how can we extend these methods to have out-of-the-box data validation in ML pipelines using these types of ideas. And of course, in blue, we have some theoretical results just to satisfy our curiosity as to why on earth all these things work. But I'm not going to go over any of those today. Okay, so first I'm going to start a little bit with HoloClean. Everything started from there. And I want to highlight some key components of really, our journey from traditional probabilistic graphical models to modern attention-based methods that helped us automate data cleaning. So as I mentioned, HoloClean was a project. It started back at Stanford when I was a postdoc. The first publication appeared in 2017. And the whole premise was, okay, we have tabular data. This is a snippet from a real-world data set on trips of taxis in Chicago. You can see some attributes like the pickup tract and the pickup lat and long. And we wanted to find a way to model this data, find a probabilistic model for this data, and start reasoning over this probabilistic model. So the whole idea here is that you can talk about each cell as a random variable. You can capture statistical signals like co-occurrences across values very nicely. And you also might have domain constraints that introduce more complex dependencies now across tuples as well, and individual cells of tuples. So all these type of signal and structure and dependencies, you can model it using a probabilistic graphical model that can capture both the local features, the domain constraints, It is a great fit because it's, it captures the sparsity of tabular data as a first-class citizen, and it was a great start. However, it had significant limitations. To scale inference over these models, we actually had to perform several tricks. We couldn't rely on GPUs and accelerators and so on. And we had to actually go back to our friend logistic regression by relaxing some of these constraints to be more like individual features. Also, you need to have the users encode explicitly this type of domain constraints, like the red ones shown here, that lat and long determine basically your tract. And it was also limited to categorical data because inference over mixed type of distributions over these models was not a solved problem. So this was take one. It worked quite well, but it had all these limitations that, whenever we were trying to put it in the hands of users, they would always complain for one of these three issues. So how do we go about removing all this? And we took a step back and we started saying, wait, why don't we just, use a simple attention mechanism to see if we can capture dependencies, schema-level dependencies between attributes. So the encodings here, you encode your values using your dense embeddings and whatever you want. But now when you want to find these contextual representations, you will restrict the attention mechanism not to operate at the value level, but operate at the schema level. So the goal here is to say, I want to predict back a target attribute, and I want to find the most important attributes that I need to consider to learn how to predict these things back. So if we are to dive a little bit into the specific architecture of this mechanism, really, if you see here in the softmax equation, the only difference compared to the standard, self-attention mechanisms is that we take into account the embeddings of the schema. The query and the key correspond actually to the type of the attribute that you have, and the value is your normal value and so on. So apart from that, there's nothing more than a dot product attention mechanism. The more interesting thing is to ask yourself, why the attention mechanism? And, empirically, we found that actually the attention mechanism could capture very well dependencies like the ones in the graphical models. So here is actually an attention matrix learned by HoloClean for the same data set. And without encoding the domain constraint that, the lat and long determine the census tract that you have. In fact, a bounding box around the lat and long determine that. The attention mechanism at the schema level is able to capture that dependency and find it from data. And if you think about it, there are these excellent papers that you can tie the attention mechanism back to graphical models very easily. Graphical models are nothing more than kernels. And Francis Bach and Michael Jordan showed that in 2002, they showed how to use kernels to learn graphical models. And then later on, there was this recent paper that showed actually that you can start understanding and reasoning about the attention mechanisms through the lens of kernels. So actually, these two models are actually very related. Does it work, this thing? Well, if we focus back on the data set, and this data set, by the way, was something used by Google to benchmark their data validation tool called TFX. So what you see here is a snippet of the data set. You see the missing values for different companies. And the interesting thing to observe is that you don't have exactly the same lat and long, but you actually have kind of a box that should imply the same census tract. And if we apply this type of approach, this HoloClean with the attention mechanism versus other methods that range from HoloClean, traditional HoloClean with quantization, methods like XGBoost, denoising autoencoders, generative adversarial networks, name it, you see that actually just with that simple architecture, one level of attention, nothing more, we get a boost of more than 40% F1 points improvement over the next best method. And not only that, but we're actually 10 times faster in analyzing this data and predicting back and fixing these mistakes. So this was a major win, basically, that this type of thinking and understanding gave us this more advanced platform that we later applied to a bunch of use cases. Here is an example of a data categorization case where you have market research data. This is about purchase transactions. They're missing some SKU, and you want to actually identify what was actually purchased. This was from a collaborator. They were using a lot of human hours to actually clean this data and fix these mistakes. And what we found is that actually months, not hours, months, sorry. And we did it in less than 15 hours for the entire data set they have with an accuracy of 97%. And for the case when we were wrong, actually the humans, where there was a disagreement between what the human did and the system did, most of the times you can see actually here that the ground truth was incorrect. 70% of the time, what the humans had labeled as correct was incorrect. So this was a very interesting result that we found. And of course, we applied the same kind of techniques to a bunch of different data quality problems, including error detection in demographic data, where you find this kind of weird discrepancies with respect to zip codes because the areas are entangled, KPI tracking, imputation of numerical data setting for industrial monitoring, and so on and so forth. So this was a major realization that structure there, we actually didn't need humans to specify it. We were able to go from these probabilistic graphical models that took into account domain and business logic to models that you just feed in the data, you get back this excellent model that you can use for all your downstream tasks. Now, building on this, we started asking ourselves more recently, okay, we saw that you can fix all the mistakes and perform these analytical tasks with higher accuracy and so on. And these are standard traditional analytical tasks. We started thinking, wait, why don't we just try to extend this model and perform kind of out-of-the-box data validation for ML pipelines? So we introduced this system called Picket. The whole idea of Picket is basically, we want to design it as a plugin that it just operates on the data being fed in your pipeline, has nothing to do with the actual model that you're training. And really what you want is kind of a filter fence. Right before training, you want to detect outliers and mistakes in your data and filter this data out. And at prediction time, you want to try and understand, will the model give me a sensible prediction? Should I accept that prediction or reject it? So after you have a trained model, you need to accept or reject the predictions. And if I'm to be a little bit more concrete, and concrete here again via examples, the idea is to guard against data corruption in both aspects of the ML lifecycle. And for training, the goal is to detect and filter out corrupted data. We don't want to fix it. We assume abundant samples, and you'd want an automated way to just remove all these samples that will basically bias your model. And I'll show you in a bit how it works even against adversarial attacks, this approach. For inference, we wanted to actually say, hey, we want to detect what we refer to as victim samples. And victim samples are, imagine you have trained the classifier in advance. A victim sample would be an input point that you are asking your model, but you have so much noise that now the noise will actually change the prediction of the model. You don't want to detect samples for which the prediction would already be wrong. That's fine. And you don't really care about samples that if you introduce a lot of noise, still the model is robust enough. But you want to find exactly these edge cases where the model will give you the wrong prediction just because of noise. So for Picket, there are two key ideas here. One is, again, to go back into this idea of let's learn a model that captures how the clean data will look like and try to use this model to boost to actually inform our decisions. So in this scenario, we run what we call PicketNet. I'll show the architecture in a bit. It's actually a transformer for tabular data. You actually want to warm start the model for some epochs. Then for another set of epochs, but only a few epochs, you will start monitoring the loss or across the trajectory of the loss across these epochs for the different data points, training data points. And using these statistics, these loss statistics for each individual attribute in your tabular data set, you can aggregate it to build this kind of filters. And here, you actually need to truncate the tails, both the left tail and the right tail. The low part is basically to detect poisoning attacks, because they will have a lot of concentrated noise that is kind of low magnitude and targeted. And more systematic errors or random noise, they will just have a higher reconstruction loss. So really the idea is we want to learn a model that can actually tell us through this measurement of reconstruction, is the data sample corrupted or should I accept it? So you cast this problem really into an outlier detection problem over this reconstruction loss. And the model that gives us the reconstruction loss here is, as I said, a two-stream transformer for tabular data that now blends this idea of schema-level attention together with a kind of a hybrid attention that focuses on the values. And the benefit here of having these two streams is really to offer to the model enough flexibility to fit heterogeneous parts of the distribution that is formed by the sample that we have, and also use the schema level, the higher level constraints as kind of a regularization for our model. So using this trick of having this two-stream transformer, we saw something quite interesting in my opinion, which is the following. If you try to use all the robust models and kind of filtering methods and kind of outlier methods, outlier detection methods, like IF here is isolation forest, 1 class SVMs. RVA is a state-of-the-art model for robust variational autoencoders. And clean CL here indicates training a downstream model over some data using the clean samples. NF is we just accept the samples as is. What we find is using this type of filtering mechanism that Picket is offering. So really the novelty here is these reconstruction signals, not the outlier detector. We can actually, if you see, we can, the downstream accuracy, if we train a model now just after we have filtered the points that Picket selected, the downstream accuracy is actually much better than accepting the noisy data. It's much better than filtering data points with other state-of-the-art outlier detection mechanisms. And at the same time, it's actually very close to training with a clean training set. If you see here, the discrepancies are quite small with respect to the accuracy. And for example, for neural networks, you can go from like if you trained on the raw data, your accuracy for for one would be 67, for the other data set 86%. Then with a clean one, you would have this increase of a little bit less than 10 points. You can recover that with Picket. I should mention that these are poisoning attacks. These are hard attacks that aim to destroy basically the performance of the downstream model. But Picket is able to handle this quite gracefully. So again, in Picket, really the idea that we followed is nothing more than the same two-step approach that we had followed in HoloClean, where we say, hey, let's use the context, both the value level dependencies and schema level dependencies, to learn a model as to how the clean data should look like and try to identify errors just by considering our reconstruction loss. So the inference was over this reconstruction loss. So these are the two systems that I wanted to highlight. But before we close, I'd like to mention briefly a little bit as to what is next. So the thing that I'm most excited about is to be able to apply all these techniques of automated data quality ops to really heterogeneous and open domain data. And this focus is really on knowledge graphs. So in knowledge graphs, you can have information that has to do with, that comes from images, from text, information that is encoded as structure. You have semantics now that is not the fixed schema that you have, but really you can have a very diverse and open domain schema that you need to reason about. And not only that, one could argue that, okay, what would be the model, the equivalent model I'd use? Fine, I'll just use graph embeddings or graph neural networks and embed everything and so on. The big problem here is that you have to reason about hundreds of millions of entities in real world knowledge graphs and tens of billions of facts. And the biggest challenge is how can you scale graph learning? And the whole idea here is to really optimize the resource utilization of the system. So recently we started this exploration. This is with a colleague from Wisconsin, Sivaram Venkatamaran. And we introduced this system called Marius, where our goal is to really introduce a scalable no-code graph learning system with the goal of enabling learning these graph embeddings over billion edge graphs in a single machine. And downstream applications, now you can have this nice data cleaning, data validation, and imputation and so on applications over these models. And the secret sauce here is really a new data replacement policy that we introduced, and also a new architecture for the system that utilizes pipelining. And the whole idea is to start storing these large embeddings on disk and be able to pipeline things fast to CPU and GPU memory to achieve very high utilization really of your accelerator, of your GPU. So for instance, here you see a comparison, FM2 against PyTorch Big Graph from Facebook, DJL from Amazon. You see that, their GPU utilization is not the greatest. For DJL, you see below less than 20%. PyTorch Big Graph around 30, maybe sometimes a little bit higher. But for our system, we can achieve kind of consistent utilization of this above. If you are operating in memory, it's above 60. And for, on disk, even on disk, you can have high utilization. So the goal here for this system, actually, this is open source. You can download it and visit it at mariusproject.org. The whole idea is this is the first step towards that goal of enabling these models over heterogeneous structured data to be able to support downstream tasks. Okay, with that, I would like to thank you and close just again with the same message. Just learn a generative model over your data in an unsupervised or self-supervised fashion, and then just use that to run inferences, and you can actually automate data quality ops using that approach. Thank you.
Awesome. Thank you so much, Theo. Really great talk. You covered a lot of ground, so I'm sure we'll have a bunch of questions. For folks who are in the audience, feel free to put your questions in chat and we'll try to get those to Theo. Yeah, so I guess just kick us off. One thing I was curious about, I think you kind of brought it back at the end, like just train a general model and kind of use that for maybe the data validation cleaning task. I'm curious what kind of noise distributions are you able to handle really well today? And like that would be my first question, and maybe I don't know how to scope it more narrowly, but like, what does it really work on? And kind of like, I think the second thing is maybe a little bit inspired by like a lot of recent interest in like robust machine learning, like what are cases where maybe there are systematic variations in your data? So there are a lot of modes in the data distribution, and perhaps like methods like Picket might discard some of those modes during training. Do you have any thoughts on that, and maybe like any results there?
Yes, actually both. So let me tell you about the types of noise that we can handle. So the types of noise that we want to be able to handle, first of all, in real world data, you cannot really make assumptions about the noise. I can tell you that in many cases you have types of noise that can be random because a human performed a mistake. But in many other cases, exactly because you're relying on ETL approaches, you actually have systematic errors because you're integrating information across different sources. One example in this Chicago taxi dataset, the missing points and the offsets of the representations was because this data is aggregated over a bunch of providers and taxi companies that they measure things in a different way. So we want to be able to handle random noise. We want to be able to also handle systematic noise, where systematic here means you will see repeated instances of this noise, and typically has, if you condition on some kind of attribute or setting, it is not random anymore. And then you also want to even handle, in the Picket case, settings where you have adversarial noise. And adversarial here, I'm talking about cases where you are aware of the downstream task and you want to actually go and attack that system. So for HoloClean, actually in our MLSys paper, we showed that experimentally that for the first two types of noise, not for poisoning attacks, not for adversarial cases, but for both systematic and random noise, this type of structure, this attention mechanism, handles it very gracefully, exactly because it can pick up these types of strong biases, if you will, as to what the clean data should look like. For Picket, the results that I showed there actually were with the worst possible case noise, poisoning attacks against models. And the trick and the reason why the model was able to distinguish between, filter this out is because of early stopping. So by having the attention mechanisms and again, picking up the structure, you don't give the model the chance to overfit to all these examples, but that strong bias and regularization bias that you're introducing with the schema-level attention kind of helps the model at the very early stages of training not to overfit to this type of adversarial noise. That's the empirical findings and the types of noise we can handle. In recent work, and that theory work that I mentioned specifically for robust mean estimation, we actually compare against many robust estimation approaches that the mitigation mechanisms is just throw away a sample. And we saw that if you know, again, the structure and you utilize that, you have all these, you can tolerate even stronger attacks. And the strongest attack possible is to allow the adversary to change arbitrarily as many samples as they want and any coordinate they want. Standard robust ML will assume that a certain percentage of the samples is corrupted. In our case, all samples can be corrupted, but not all coordinates, so that you can recover through these types of dependencies. So we have some theoretical results there as well as to, you can tolerate very, very powerful adversaries and types of noise if you utilize structure.
I was as kind of a follow-up to that, one of the things I was wondering is, how do you handle cases like where maybe you just have a very different mode of the data where there's a teeny bit of the data that acts very differently from everything else? How do you kind of distinguish between those, I don't know what you call them, like clean outliers versus just the data that actually has some problem with it?
No, this is actually a great question. This is still kind of a problem, if you will, because you might have actually cases where the structure is different. The only solution that this is something that we're actually investigating, in the long tail. But in Picket specifically, we introduced these two streams, both the schema level and the value level. And we found through ablation studies that really the value level can allow you to be a little bit more robust towards cases like the one that you are describing, because this is the value level attention is really is a kernel that captures the specific value dependencies, it doesn't enforce a higher level structure over the dependencies. And we can find some kind of mitigation there. It's a little bit more robust. There are profiling mechanisms actually that you could potentially use to identify how you can split an initial sample into kind of homogeneous samples, and then you fit individual models, and in reality, that's what you would like to do.
Thanks so much.
Yeah, I actually have a question that is a little bit specific on the models that you presented. If I understood correctly, you not only, let's say, encode the values, but also encode information about the schema in the form of like embeddings for columns. Is that what I'm actually?
Exactly.
So that's very interesting. Again, I'm curious if you could comment on, like, for instance.
So this is the architecture.
Yeah, exactly.
Yeah.
So I'm curious if you can comment about the rationale, the intuition of this, and also one thing that I was thinking about is this sounds specifically fitting for when you have kind of the same data types across the board. What about heterogeneous data types? How would this be impacted by something like that?
No, so this is great. So what is the hope of this self-attention at the schema level? So here, for instance, we have, the value stream attention. I think I have flipped here H and Z in the call out, but bear with me. So the whole idea here is that for tabular data, let's start with the simple case of tabular data, and you can see it actually in this setting. You have these higher level constraints that regardless of what is the value that you're observing, they should hold. Think of them as invariants that are over the semantics of the data set. So it doesn't matter what kind of different values census tract takes, but whenever I see the same lat long values, they better have the same census tract, just because of the geography of the problem, right? These constraints, you can either encode them as, in databases, you would encode them as functional dependencies. Or if you have a lot of non-corrupted data, you can actually pick them up through these types of attention mechanisms. And the interesting thing is that back in the day, we would rely basically on users specifying them. But then we saw that performing this type of schema to schema, attribute to attribute, really. So basically just using the positional encodings, this type of attention mechanism, it was surprising that actually you can recover those. In fact, I have another empirical result that I cannot prove yet, which if you do structured learning over the data with targets over finding this kind of high level approaches, you get exactly the attention matrix that you will get from by fitting the data over your model. And the first one, you can actually do it much faster and in a much cheaper way. So it's still, it's quite interesting to start thinking around these types of different kernels that you can encode in the attention mechanisms. And that's why I find that paper from Russell Akutnikov had that paper that I mentioned as to interpreting transformers through the eye of, through the lens of kernels. That's really where you can start thinking, oh, why don't I encode all the different semantics and so on and so forth. Now, in the case of heterogeneous data, I expect that the same kind of attention mechanism can potentially hold for graphs. Let's take the example of a graph. The way you can, again, tackle this heterogeneity and not have a huge attention kernel is by running some of this structured learning type of profiling that I mentioned before, identifying kind of homogeneous areas that have this type of structure as a pre-processing step, and then fit these heavyweight attention mechanisms and models over these parts of the distribution. So you do this kind of, think of it as I'm filtering away all the attributes that are irrelevant for now, and I'll keep only the relevant ones. Then I can run my transformer over that part of the heterogeneous data set. And this is something actually that we were doing heavily in HoloClean and at the company as well for being able to scale, because you can distribute all these individual models now as well.
Oh, interesting. So this is also not only like a better way to do that, but also a more scalable way to do it.
Exactly, because you can say, it's basically, think of it as vertical partitions over a tabular data set, and then I split it and I learn individual models.
Got it. Interesting, very interesting. Thank you.
Hey, Theo, great talk. I had a question. So you talked a lot about imputation or filling in missing values, but I think in a lot of settings, people also just want to monitor data and see if something is going wrong in one of their data pipelines, because usually, at the end of the day, you want to have reliable data. You want to build a pipeline that gives you reliable data, and you don't want to have to clean it each time you work with it. But you also want to detect when something goes wrong. So I'm wondering, how that setting is different, and whether you can still apply some of the same ideas, or maybe some of the goals change.
You don't change the goals actually. So if you have this generative model, you can convert the problem of imputation to actually an error detector by saying, hey, I'll pretend I don't have this value. What should I see? And then you can start comparing the predicted value against the initial value, if you will, or what you have. And this is actually how we use these mechanisms to perform error detection and outlier detection. So this kind of reconstruction, if I have enough signal and context to reconstruct my value, do I have enough redundancy, and structure to reconstruct it with super high confidence? If yes, and it is different than my initial value, the one I observed, then it should be an outlier. And we use all these mechanisms to actually not only, you can do a couple of tricks there, Matej. You can either use it to automate outlier detection and error detection, or you can also use it to prioritize errors that you want to surface to humans, or errors that you believe that the model can tolerate, and you can even apply automated imputation and so on and so forth.
Okay, got it. So that gives
it's the
you
same strategy.
It gives you enough information about the likelihood that you can actually find errors.
Exactly.
Okay.
Exactly. And the more dependencies you have, the more the better your estimate will be. So that's really the premise here.
Theo, I wanted to highlight one of the questions from the audience. So Sanjeev Kumar was asking about that first slide that you had up with the notorious data quality problem with all the other commercial companies on it.
Yes.
I'm wondering, can you help us kind of relate how HoloClean and Picket and I guess Inductive fit into that whole startup data quality ecosystem?
Absolutely. So these problems of data quality had always been there, and people have been focusing on using more manual approaches or more approaches driven, with respect to transformations and ETL and rule-based approaches. So most of the traditional kind of players in this space would focus on transformation and data preparation workloads, where the goal there is to hard code a bunch of rules and apply them at scale. So in the, I would just, and there are actually a lot of companies that provide this type of scaling of applying these rules to your data. From the database community, there are actually a lot of startups that try to focus on specific problems related to data quality. For an example being, for instance, Tamer. In Tamer, they focused explicitly on the problem of identifying and finding duplicates in records, which is a specific instance of a data quality problem. There were other companies like Trifacta that focus more on data wrangling and then identifying, via examples, you can actually infer some of these rules that I mentioned before to actually kind of prepare and clean and standardize your data. And there was this big gap of automation and utilizing AI to power kind of a more general platform around both error detection and fixing some of these values and mistakes. For instance, and that's where basically HoloClean and Inductive came in. There are a lot of companies that will focus on very specific and targeted problems, and these aspects are kind of niche. And one aspect that was not, nobody was targeting at that point was basically that of really automating this kind of reasoning, if you will, over noisy data. So our positioning around Inductive was really about reasoning over noisy structured data.
Theo, to ask a quick follow-on to that, actually. So one thing I'm curious about is, like you mentioned, that maybe traditional data cleaning and validation pipelines are rule-based or rely on kind of humans to write down exactly how they want to encode rules about their data. I guess one advantage of that is that it's pretty clear what the logic is that's running to actually do the cleaning. And I guess in some of these approaches, one thing that makes me nervous is what is it actually trying to do? And is the imputation that's doing kind of robust across, changing distributions of data, changing like upstream pipeline changes when you're doing ETL or so on. So I'm just curious, like, are there challenges there that you've seen in industry or even like in practice, in applications that you could talk through, and just generally what that issue looks like for you?
So auditing is a big challenge there, and nobody wants to accept an automated chains. That's the biggest challenge of why should I accept this change? It will destroy everything downstream. And what is the model doing? But if I had a rule, I would accept this change, right? So how do you attack this point of view, and how do you change it? One, you need interpretable models. And if you saw in the attention mechanism, the schema-level attention, actually it is interpretable, because I know the semantics of the attributes, and I'm telling you I'm paying attention to these things. And because of that, I'm putting a lot of weight, and because of these values, you can actually have an interpretable model. That's the first aspect. The other aspect is to allow people to not necessarily accept immediately in an automated fashion what the model is suggesting, but demonstrate that you follow probabilistic semantics, and you have this kind of confidences over the predictions of the model. And based on these confidences, they can calibrate it and accept automatically things that they feel, oh yeah, this makes sense. And because I knew the semantics and I have a confidence, I will accept it, versus I will just want to audit it, and it's nothing more than a way to pick, the examples in the haystack that I want to look into. There is a lot of interesting work how that affects downstream tasks, and there's a lot of work to be done there with respect to sensitivity. And I don't have a good answer yet to, unless your task is very well defined, kind of aggregates over the data that you have, or a predictive model. There is still this question of, will it break my model? Will I learn the biased model if I start removing data? These approaches towards Picket, and the results that we're having on the theory side they're trying to address these kind of challenges. From a practical system, the last point I forgot to mention, I just wanted to bring it up, is that you don't want to rely only on these statistics that you learned, but you want a framework that beyond these attention mechanisms will allow users to also introduce these high-level business rules, and business logic, and reason about that in a holistic way as well. So let me flash quickly really the architecture of this AIM network, just to highlight one aspect. If you see here this red part that I'm referring to as external context, this is basically the external features that HoloClean would allow you to incorporate.
It's super interesting, Theo. I'm curious, like, in which this additional context, how is it actually provided? Is it in the form of rules? Is it in the form of features? Because in this case, it looks like probably it's more features.
So we are like HoloClean supports basically either first order logic rules, so implications, and then you can take these rules and convert them into features so that it's kind of scalable. This is pretty standard actually in graphical models, the way you would relax this into features. And we would also support matching functions. So if I have an external catalog and for certain individual values, I need to obey a specific value. So all these types of external context, there are adapters in the system that enable that.
Maybe this is a silly question because I really don't know enough about the field, but I'm curious, like when you are in situations where like that, like where there's an external catalog, or maybe even like the example that you were showing us with the like zip code and lat long, I'm curious, isn't there sometimes ambiguity, like which one do I trust, right? If I have a rule that says the zip code should imply my long lat, or my long lat implies my zip code, is there a mechanism baked into that tells me which one I should trust more than the other?
So the way we handle this case is basically by really creating an ensemble at the end of all these features, and allowing if a user wanted to kind of create kind of a cascade, not more of a weighted vote, they could. In many cases, actually, we found that people really believe their rules and really like their rules, but their rules are wrong, or they wouldn't capture corner cases. And then you would have the system firing, hey, and with super high confidence, this is the value and so on. So again, there you want to enable additional tooling on top of what you're building to allow for auditing. Like that's really the only way to get around this these questions. You need to give power to the users of the system to do this.
Got it. That makes a lot of sense. Yeah.
But in many cases, actually, we would discover rules that the user is like, oh, this makes sense. I didn't think about it. I'm like, great, let's put it in. You know?
Theo, I wanted to ask you about a use case that is probably a very far future work, given kind of what the systems and the examples you've been talking about. Have you put any thought into how you would handle things like images or videos or you know, much more high dimensional data than kind of your traditional tabular data? For example, like one of the weird things about these image models is that you can throw random noise at it and nothing happens, but you like do some weird noise and adversarial things happen. Have you thought about any of these things, or is it kind of you know, closer to a pipe dream at the moment?
A student of mine is suffering to answer these questions. I would say we actually started looking at it very recently. Especially there was this interesting model that came out recently that applies transformers over images. And we started thinking about this. I do not have a good answer for the type of noise that you mentioned. I have a good answer for something else in the image space, and that has to do with semantic segmentation. In that scenario, we have actually deployed that in another project that we have about parsing the scientific literature and segmenting PDFs. You can do a very simple trick that you can bring all these structure kind of ideas, allow a deep learning model to predict classes and labels for the different components in the image. But then you can have kind of a post-processing, post-smoothing basically model that will go and identify misclassifications of the base model and kind of fix them by considering these dependencies. This is not really going into the visual space, if you will. It's really kind of a you know, naive application of these ideas on the image space. But I found it quite interesting. There is actually a theoretical work by Ben Recht at Berkeley recently that talks about this kind of hidden dependencies over the input samples, and I would highly encourage you to look into that. But yeah, the first part hard. We're still trying to figure it out.
That sounds cool. I look forward to what your poor student comes up with.
He's awesome. He'll come up with awesome stuff. He's the one that came up with Picket Zifman. Yeah.
Theo, last question. Just want to get your take on what you think about kind of maybe the learn everything type of approach. Like, you know, like GPT-3, for example, is actually pretty good at denoising English as an example, right? So do you have thoughts on just like that general flavor of method? I think it's kind of related to some of your graph and knowledge-based work.
Yeah, I'm very fascinated by these methods, and you know, while every time I'm expecting that, okay, you have memorized everything, and you expect to observe this type of, you know, in quotes, stupid memorization, you actually see very cool you know, things coming out of these generative models. It is a great approach. One thing that always worries me a little bit, and I feel that it is something that especially people in academia we should take into account, is kind of resources and being able to allow, you know, even scientists having access to these types of powerful modeling approaches, not necessarily GPT-3 and the approach. So designing systems and tools, for instance, Marius in this case, you know, our goal was really, hey, I just have a node. I cannot go on AWS and spin, you know, 16 nodes with 8 GPUs each to just train one thing. And if you can do these types of models, so it goes a little bit into kind of resource-aware type of systems. If you can do that without, you know, learn the same models without boiling the ocean, if you will, that would be awesome. Yeah.
Awesome. Yeah. Sounds like a worthy cause. Yeah, thank you so much for joining us today. Really enjoyed hearing your thoughts on this area, and it was a great talk. I want to thank also our audience for tuning in today. And if you haven't already, go to our website, mlsys.stanford.edu, sign up to our mailing list, subscribe to our channel. And yeah, next week we have, Dan, do you remember who we have next week? Sorry, I'm blanking.
Next week, we've got Amit Tawakar from CMU.
Awesome, yeah. So see you all next week. Thanks, bye.